So now we'll find the expression for another thermodynamic potential, which is Gibbs free energy, denoted by capital G. So if you remember, for the Helmholtz free energy, we defined Helmholtz free energy for a system, thermodynamic system, which is at constant volume and constant temperature. That is, any process has to be isothermal and isochoric. Okay, now here we'll express this Gibbs free energy for an thermodynamic system which is at constant temperature and constant pressure. That is, any process has to be isothermal and isobaric. So let us consider a system, okay, which is undergoing a transformation from initial state I to final state F due to an isothermal and isobaric process at constant temperature T and constant pressure P. Okay. Now let Vi be the initial volume of the system and Vf be the final volume of the system. So what is the work done by the system during this transformation? It is delta W equals to P delta V. Now as the process is isobaric, P is constant. Thus it will be P into Vf minus Vi. The P remains constant throughout the process. Now, since the process is also isothermal, now we can use the following relation from Helmholtz free energy. Okay, so since the process is isothermal, we can use the following relation for Helmholtz free energy. And what is that relation? Which is delta W is less or equals to minus delta F. Okay. Or now let us put the value of delta W. It is P into Vf minus Vi. So P into Vf minus Vi, which is less or equal to, what is minus delta F? It is Fi minus Ff. Since delta F is F minus Fi. Okay. Or P into Vf minus Vi less or equals to, now let us put the values of Fi and Ff. So we know Fi is Ey minus Tsi minus Uf minus Tsf. Okay. Or now what we'll do, we will bring all the terms for the final state on the left hand side and all the terms for the initial state on the right hand side. So what are the terms for the final state? Okay, so this PVF term. Okay, so if we remove the bracket, it will be PVF. Okay, this term, then this UF and TSF, this term. Okay, so it will be P on the left hand side, it will be PVF. Then if this whole term come on the left hand side, it will come as plus. Okay, so plus UF minus TSF. Okay, and then we will bring this PVI term on the right hand side. Okay, so if it goes to the right hand side, it will go as plus, so plus Vi, and we already have this term on the right hand side, which is Ui minus Tsi. So next, in the next step, we will remove the brackets and we will rearrange the terms. Okay, so rearranging on the left hand side we have U F minus TSF plus P VF, which is less or equal to U I minus T SI plus P V I. So now if you look at both the terms on the left hand side and right hand side, you see that they are of same nature, okay, which is U minus TS plus PV. Okay, so now we can introduce a new function. So now introducing a new function G equals to U minus TS plus PV. Okay, so GI will be this new function for the initial state. GI is will be UI minus T SI plus P VI, and this new function G for the final state will be UF minus T SF plus P VF. Okay, so if suppose this is our equation 1, so putting our values in equation 1, or from equation 1 we get, so UF minus TSF plus PVF is GF. Okay, so on the left hand side we have GF, which is less or equal to, on the right hand side you see this is GI, so it will be GI, or GF minus GI, if we bring GI on the left hand side it will less or equals to 0. Or so what is GF minus GI? It is the value of the new function f at the final state minus the new function in the initial state. So it will be change in the new function, which is delta G, less or equals to 0. Okay, so thus this new function G defined by G equals to U minus TS plus PV is called Gibbs free energy. Okay, and GF is less than GI. Okay, and where this inequality holds for irreversible process and the equality holds for reversible process as usual. Okay, so for any, and if you remember we define this Gibbs free energy G for a thermodynamic system which is at constant temperature and constant volume. Okay, so that is any process has to be isothermal and on constant temperature and constant pressure. So any process for which the system undergoes has to be isothermal and isobaric. So for any isothermal and isobaric process, the Gibbs free energy for the final state has to be less than, or it cannot exceed the Gibbs free energy of the initial state. It is less than the final state. This value at the final state is less than its value at the initial state for irreversible process, and they are equal for reversible process. That is, for a reversible process, for a reversible isothermal and isobaric process, there will be no change in Gibbs free energy, and it is defined by G equals to U minus TS plus PV.